So section 9.1 is going to discuss differential equations. So it's kind of cool that you're getting exposure to this early on in your calculus career. You've actually probably solved differential equations in Calc 1 maybe a little bit, although you might not have realized it. Now I'm actually going to begin this by asking you a question. What's a topic in the news? Something that's been, I don't know, kind of big lately. Is there anything that comes to mind?
COVID.
Corona.
COVID, yeah. All right. Now this video might be a little bit dated now, but hopefully it's still going to be worthwhile looking at. Let me take a quick look at an article that might be related to COVID, and it's the spread of illness. Now you studied this in epidemiology, and it's actually a cool subject, the study and spread of the causes of illness. Yeah, I didn't say that right. But there's several things that are going to be involved in any model, and they boil down to an acronym called SIR. The S part of it is going to be the number of susceptible individuals over time. So let me see if I can zoom in a little bit. There we go. Susceptible individuals over time. Then there's the number of infected individuals. So that's this part right here. And then R is the number of recovered individuals. Now, I'm not going to go into these differential equations too much, but I do want you to think back to something from your Calc 1 days, and that is the sign of something, the sign of the derivative. Because this is the derivative of I with respect to R. So it's how the number of infected individuals is changing. So what can you tell me about the sign of a derivative and how it reflects on the function? In particular, if the derivative was negative, if the derivative of I with respect to t was negative, what's that telling you about I?
Decreasing.
It's decreasing. Good. Now that simple question is something that I can and maybe even will quiz you on. What is the derivative, the sign of a derivative of a function tell you about a function? If it's increasing or decreasing. Now, right here, suppose that we could make this term negative. Then that would mean that the number of infected individuals would be decreasing. So that'd be great if you could decrease the number of infected individuals. Now, it's not necessarily mean you're going to go down to zero right away, but at least you're on the right path, and eventually you'll get there. And you're going to get there by wearing a mask and by social distancing. You look what's happening in other states, and I hope you realize that we're lucky that we did things right in Michigan. We didn't open up too soon, but we're starting to go back the other direction, have been for about a month. So keep your social distance. It's a favor to you, it's a favor to healthcare workers, and a favor to people around you. It's just that important. It's not that hard. But we're here to discuss differential equations, so let me get busy on that. There's actually one that you've dealt with the results of for quite some time, and that is this. dP by dt is some constant times p. Now, what's this? Well, there's actually a range of different options that this could reflect. This could reflect population growth. And how is that? Well, the rate of change of the population is going to be proportional to population. So if there's a growth rate of 1%, 1% of the original population, that's going to be how the population is changing. It could be your bank account. So investments or interest on investment. Your compound interest. How much money you get in interest, the change in the value of your account or the change in the principal is going to be some interest rate times your principal. Or another one would be radiocarbon dating. Radiocarbon dating. That's another one where the amount of radioactive decay is going to be proportional to how much you have there to begin with. So let's actually solve this and see what you get. So if I wanted to solve this for P, what I'd probably do is start out by multiplying both sides by dt. So dt and dt. I get some cancellation on the left-hand side. dp equals kp dt. Nothing cancels on the right-hand side. But if I want to get all the right parts together, I'd want to put the p over on this side. So I'll divide both sides by p. And that looks nice. But then I realized I can do something useful and interesting over here. When you're working with an equation, as long as you treat both sides the same, you'll probably be in good shape. And what I want to do is I want to integrate both sides. And what that does for me is it gives me, well, the natural log of p equals a constant, which is our k. And that's a k, I know, my k's look terrible. K times t plus another constant. Now suppose you want to solve for p. It's like, no, I want an explicit expression for p. Well, we can take the exponent on both sides, exponentiate both sides. On the left-hand side, I'll end up with p. On the right-hand side, I end up with e to the kt times, well, e to the kt plus c. Let me rewrite that like this.
Where did the t come from?
When I integrated. Because really what I've got here is k times dt, or k times 1 dt. And so what do you differentiate to get 1?
Oh,
well,
right.
It'd be t.
Okay.
So, and then the k is just a constant still. Remember, when you multiply things with the same base, you add their exponents. So usually we do things in this direction. Say, okay, well, this times this, we'd add the exponents. But I can split it up like this, and you'll see me do this several times here today, that I'll split this up as e to the kt times e to the c. And here's where mathematicians just get a little bit lazy. I don't know, lazy is such a harsh term. Let's say we employ a little economy of movement. E to the c, that's just another constant. So I'll call that a constant and I'll put it out in front there. And there we go. There's your model. This is a model, a very simple model for population growth, radioactive decay, interest on your bank account, continuously compounded interest, etc. And what happens is that sometimes they'll tell you an initial condition. For instance, they say, oh, well, P of 0 is 2,000. Your initial investment, your initial deposit in the bank was 2,000. And that information is going to allow you to solve for that C. So if I put in a 0 for T, I'm going to get 2,000 for P. So 2,000 would equal C e to the k times 0, which is e to the 0, and e to the 0 is 1. So that tells me my constant is 2,000. And then I can put it in your model here like this. And so that model, if you update it, might be P equals 2,000 e to the k times t. Now you need some more information to solve for what k is. K could be your interest rate. K could be a growth rate if you're talking about populations. Could also be a decay rate if you're talking about, again, populations or radioactive decay. But this is just a feel for some of our work with these types of problems. Now, in this section, we're not actually going to be solving for our differential equations so much as maybe checking for solutions. So let me show you a little bit about that. Let's look at this one. So I'm going to write down a differential equation. 3 times y double prime plus 20 times y prime minus 7 times y equals 0. And let's keep in mind that this really represents the second derivative of y. So 3 times the second derivative of y plus 20 times the first derivative of y minus 7 times y, that equals 0. Now the book in this particular case was kind enough to say, you know what? I think a solution to this would be of this form. So it's going to be something of the form e to the r times x. Why don't you see if you can't solve for the particular values of r that would be solutions for us here? So you're like, really? I don't know. Well, if this is a solution, we should be able to put in a couple things like the second derivative and the first derivative in here, and this should all work out nice and easy. So let's see if that's true. So let's calculate both of those things, starting with y double prime, or y prime, and then y double prime. Now I'm assuming that really this is dy by dx. And this is d squared y dx squared. So I'm assuming that I'm working with the first and second derivatives here. Someone tell me the first derivative, please.
R e to the rx.
Cool. R equal to Rx. Does anyone else look at that and think of Rx as like, oh, prescriptions? I keep on thinking of like prescriptions every time I see that, but all right. How about the second derivative? Well, it's going to be, that's a constant. Let's differentiate this again. When I differentiate e to the Rx, I'm just going to get this. Times the r that was there originally, it's going to be r squared e to the Rx. Okay, so let's put all that into this equation and just see what happens. So if I put that all into the equation, plus 20, let's see what it looks like. R squared e to the Rx, r e to the Rx, and e to the Rx. Okay. So if you notice here, I've got a common factor of e to the Rx. I'm going to factor that out for all of these. So it's going to be e to the Rx. And let's see what's left behind. I'm going to leave behind 3 r squared plus 20r minus 7. Ooh, been a while since you've seen one of these. What we have here is an equation equal to 0. And in particular, you've got this times this equals 0. One of these things has to be 0. Now, e to the rx can't equal 0. This is always a positive value function. If you look at the graphs, they always lie above the x-axis. They're never going to cross it. But this part could equal 0. In fact, I'm guessing that it's going to factor as a 3r and an r, and I don't know, 7 and a 1. Except one of these has to be positive and one of them has to be negative. So is it positive negative or negative positive? Which one?
Negative positive.
Negative positive. Good. Let's check it. First term, yes. Outside terms would be a positive 21 r minus 1r gives me 20r. And the last term checks. So good job. Now that gives me two solutions. That tells me r is 1/3 or r is -7. So those two particular values for r are going to work. They're going to be solutions for our particular differential equation. So you're okay with that part there? How we got that? All right, let's continue. Now, what the book does is it says, okay, well, now that you found these two values, why don't you check that the general solution is this. It's going to be y equals a times e to the r1 x plus b times e to the r2 x, where this is r1 and this is r2. Why don't you check that your solution, or that this is a general solution to the above equation? We're not even going to specify a and b. It doesn't matter what they are, just as long as you have e to this power and e to that power. So how does that shake out for us? Well, that's going to mean a times e to the 1/3 x plus b times e to the -7x. That's our general solution. To prove that's a general solution, we need to plug it into our differential equation. We need to plug it into this all the way back up at the top. Make sure that it fits in here. Now, in doing that, before I do that, I'm going to want to calculate y prime and y double prime. So let's just crank that out right away. Y prime, well, fortunately, that's a constant. And the derivative of this is just going to be the constant out in the numerator times, or it's going to be up in the numerator times a. So I'm going to get a over 3, or 1/3 a times e to the 1/3 x. And then likewise over here, the derivative of this is going to be the derivative of the exponent, -7 times b times e to the -7x. So that's your y prime. Y double prime, let's see, well, differentiate again. So again, I have another 1/3, so it's going to be 1/9 a e to the 1/3 x minus minus is going to be a plus 49 b e to the -7x. So there we go. We've got y, y prime, y double prime. Let's put that all in to our equation and calculate all this and see if it actually works out. So let's take each of these. Here's my y. That's going to go in here. Here's my y prime. That's going to go in here. And here's my y double prime. That's going to go in here. So 3 times y double prime, that's going to be 3 times 1/9 a e to the 1/3 x plus 49 b e to the negative 7x. Now I need y prime. So it's going to be 20 times 1/3 a e to the 1/3 x minus 7 b e to the negative 7x. And last but not least, I need y, which is going to be a e to the 1/3 x plus b e to the negative 7x. Somehow or another, all that's going to work out to 0. I can certainly understand if you might be a little skeptical, but let's see. And let's kind of give ourselves a little bit more room to look at things. So I'm going to need to distribute here. 3 times 1/9. Let's simplify that. That's going to be 1/3. So it's going to be 1/3 a e to the 1/3 x. 3 times 49 is going to be 147. B to the negative 7x plus 20 over 3 a e to the 1/3 x minus 140 b e to the negative 7x minus 7 a e to the 1/3 x minus 7 b e to the negative 7x. And hopefully that's all going to equal 0. Good. Looks like a long shot at this moment. All right. Well, believe it or not, there's like terms here. Everything with an a, e to the 1/3 x, those are your like terms. Let's add them up. 1/3 plus 20/3. 1/3 plus 20/3 gives me 21/3. What's another name for 21/3?
7.
7, yeah. And guess what? So I have 7 AE to the 1/3 x minus 7 AE to 1/3 x. These terms cancel each other out. Whoa, that's too cool. And let's keep going. These are also like terms. 147 minus 140 is 7, minus 7 again, remarkable. All that cancels. And you're left with 0 equals 0, which is what we were hoping for. That's just too cool. Woohoo! Nice, nice. All right, Comments on that first one? So let's continue with another kind of differential equation where the goal really is just to verify things. So the differential equation is this one, t times dy by dt equals y plus 3t squared sine of t. In this one, they ask you to verify that the given solution actually works. So verify that y equals negative 3t cosine of t minus 3t is a solution. Now, I think WebAssign breaks this up into two parts, so I'll do likewise. We're going to look at the left-hand side of this equation, and we're going to look at the right-hand side of this equation. So as far as the left-hand side is concerned, I want to take t times the derivative of this expression. So let's work on that part. So y is negative 3t cosine of t minus 3t. Let's first calculate y prime, which of course would be the same as dy by dt. So y prime dy by dt. And oh boy, been a while since Calc 1, right? Got to think back. What do I have to be careful of in particular when I differentiate this? What do I have to take care to do?
Product rule.
Product rule, good. So you can kind of regard that as your first and your second, so your f and your g. I need to calculate f prime g plus g prime f. Now let's not forget to differentiate this when we're all done. So it's going to be, derivative of this is going to be negative 3, just negative 3, times cosine of t plus the derivative of the second. Derivative of cosine is what? Minus sine, right? Minus sine times minus 3t. Well, the two minuses are going to cancel each other out. So I'll end up with a positive 3t sine of t. And could someone help out here? Differentiate that for me with respect to t?
Minus 3.
Thank you. Minus 3. Minus 3. All right. Now, there's one last thing that I need to do to calculate and verify the left-hand side or figure out what the left-hand side is, and that's do t times dy by dt. So here's my dy by dt. T times dy by dt would be, well, you'd have to distribute a t to all of these things, so it'd be minus 3t cosine of t plus 3t squared sine of t minus 3t. And I got a little bit low on that one. Sorry about that. So distribute the t here, minus 3t cosine of t. T and that will multiply there, so you get a t squared, and then a minus 3t. Cool. So that's that part. Let's work on the right-hand side. Now for the right-hand side, I got to verify what's y plus 3t squared sine of t. So, okay, well, that's not too bad. We were given what y is. Y was negative 3t cosine of t minus 3t plus 3t squared sine of t. And I can rearrange this. In fact, I can arrange it in 6 different ways, at least. So keeping this out front, minus 3t cosine of t, switching those two, I get a plus 3t squared sine of t minus 3t. So did that prove it? Well, let's take a look. Does the left-hand side equal the right-hand side? What do you think? Are those the same?
Yes.
Yeah.
Yeah, they look pretty equal to me. Cool. So it works. That's your solution. Now, the problem with our differential equations is that quite often you can't find a nice closed form solution like this. We can't often find, y equals this and say, hey, that solves our differential equation. You just can't. There's other methods you can use to start solving that. One of them is Euler's method. That's the same Euler that I've mentioned before. And also mentioned before, we talked about a little thing on Hulu called The Great, which is Catherine the Great, Empress of Russia, Tsarina. Euler actually worked for Catherine the Great. He spent a large part of his career working in Russia. So cool stuff. All right, let's keep going. Looking good with this one, I hope. Let's try some more. No, I think I got enough room for another one here. So let me use up the room wisely. And I've got that one here on Desmos, or not here on Desmos, but here on OneNote. So here's our differential equation. And we want to find out a couple things here. We want to find out for this differential equation, and let me kind of circle it for us right here. For that equation, which talks about the population of like a country or something like that, continent, the earth, city. For what values of P is the population increasing? For what values is it decreasing? And last but not least, what are the equilibrium solutions? Personally, I kind of want to start out with this. I want to start out with the equilibrium solutions. Now, an equilibrium solution is a place where the population isn't changing. It's happy. It's like, okay, we got it perfect. We got just enough people, not too many, not too few, just right. So let's copy down this equation. Let's see, we have dp by dt. And a lot of these are going to be differentials with respect to time. So that's why you got the dt instead of the dx. Because we know how things are changing with respect to time. As time continues, what's changing? Now, I hinted at this earlier when we were talking about differential equations. When the derivative is greater than 0, your function is going to be increasing, or in this case, the population is going to be increasing. When it's less than 0, it's going to be decreasing. When it's equal to 0, that's going to be your equilibrium point, where things are just staying the same. They're not making any changes. So let's see if we can find those. And basically what it amounts to is finding when this is equal to 0, less than or equal to 0, or greater than or equal to 0. I shouldn't say greater than or equal to or less than or equal to. Greater than 0 or less than 0 for increasing and decreasing respectively. The easiest thing, I think, is find out when it equals 0. That's going to be your equilibrium. So it's going to be 0 equals 1.2 times P times 1 minus P over 4,000. You might recognize this as a quadratic equation, and you'd be right. You've got this times this equals 0. One of these two has to equal 0, either 1.2 times P equals 0, or 1 minus P over 4,000 equals 0. Now in this case, hey, just divide everything through by 1.2. 0 divided by 1.2 is still 0. For this one, personally, I'd move this term to the right-hand side. And anyone suggest why I move that one there instead of the 1 over the right-hand side? I got rid of the negative. Just makes it a little bit nicer. I find that people make less mistakes when they don't have as many negatives rolling around. To solve this, I can multiply both sides by 4,000. And I get P is 4,000. So that's my two equilibrium solutions. That's where the population is just right. Either when it's 0 or 4,000. You're okay with the equilibrium one?
Yes.
Thank you. So the next part is to find out, well, where is this increasing and where is it decreasing? So again, this is just really a quadratic equation. So if you look at the graph, basically we found 2 points, 4,000 and 5,000. I'm trying to think what I want to call this. You want to just call that y equals 1.2 times p times 1 minus p over 4,000. That's what you're looking at. You want to know, where is y positive, where is it negative? You might recognize the general form of a quadratic here. And if you understand what the graph of this is going to look like, that's fine. But maybe you don't. Maybe you're like, oh, I have no idea what that graph would look like. That's fine. Let's try and do this as simply as possible. I'm going to plug in this into my calculator, except I'm going to use a P, or I'm going to use an X as opposed to a P, because X is right here on my calculator. So, okay. Hit the Y equals key. That takes you to the equation editor. We'll type in the 1.2 and then X parenthesis 1 minus X divided by 4,000. And we'll be really nice and close off that parenthesis. Now what I want to do is I want to test values, because the only place that this can change signs is in between the roots. So it can only go from negative to positive, positive to negative. I said that backwards. Positive to negative or negative to positive at the root, here and here. And if I don't know which one, that's fine. I'll just test some points. Now, hopefully you have your window set up so that you can plug in any value of X. But if you're not sure, hit the second key, then the window key. Make sure independent is set to ask. So if it's not, just go down there, make sure you press enter so that the ask independent is highlighted and dependent should be at auto. With that done, let's go to our table. Hit the second key, then the table. If there's some junk there, you know what? There's a delete key. Get rid of it. Let's delete all that. I don't know what it was from. All I need to do is test a couple points. So I'm going to test, say, I don't know, -1, and then maybe 5,000. Someone give me a value in between there. There's 1 or 2 values. Pick one of them that makes you happy.
100.
100. Beautiful. 100. Sounds good. So let's type in -1, 100, and 5,000. Now I got a lot of stuff here. Let's understand what we need. What we need is not that I got a negative 1.2 or 117 or negative 1500. What we need is the signs. It was negative, positive, and negative. That's what I wanted. Why did I care about the signs? That tells me where it's increasing or decreasing, right? So it's decreasing on this interval all the way up to 0. So decreasing on negative infinity to 0. I think WebAssign might ask you to put in a comma. You can put in a comma, that's fine. I'm really fighting with myself because I want to put in the union here, but I think it might want you to list them. And then 4,000 to infinity. That's the other place where it's decreasing. That leaves just one little interval in between where it's increasing from 0 to 4,000. So there we go. We've gotten all three parts of this. Found out its equilibrium points, where it's decreasing, where it's increasing.
On the test, could we just use decimals for this part?
You mean in terms of testing where it's increasing and decreasing?
Yeah, just for like showing our work, can we just insert like a graph?
If you did give me a good enough graph, I would take that. The challenge for you guys is going to be getting a good graph, because with this kind of a function, you need to be a little bit skilled to get it. But if you got a graph that showed really what's going on, and what's going on is you've got a parabola that's facing down essentially. So you'd have something like that, negative, positive, negative. I mean, that's fine. I get that. I would try and get a little bit good at this, because not everything is going to lend itself to an easy graph. So you might want to make sure that you can test points if necessary. Okay. And testing points might be easier at some juncture. It's just going to depend on the function. How are we looking on that one? Okay.
Good.
Thank you. Thank you. Let's do a couple more problems from the homework. I was going to do another one like that, but it's just kind of basically a repeat of the same thing. Let me just describe it for you real quick. Here, your differential equation looks like this. So fortunately, the right-hand side factors. And if you were to graph it, or if you were to test points, what you would see is that to the left of 0, it's positive. Between 0 and 2, again, it's positive. It's only between 2 and 7 that it's negative. And to the right, it's again going to be positive. So you can tell where it's increasing is these intervals, negative infinity to 0, 0 to 2, and then 7 to infinity. It's only decreasing in this one little interval right here. So that's the only place where it's decreasing. Its equilibrium points would actually be the solutions to this polynomial equal to 0. So 0, 2, and 7. So maybe not that much of a thrill to do that one. Okay. Let's take a look at another one, like one of the ones you have in your homework. I think I'm going to dial this down a little bit. They're going to give you some functions like y equals 9 cosine of x, or y equals negative 9 halves x cosine of x, and y equals 9 sine of x, etc. They're going to give you a bunch of functions. I'm not going to list them all. They're going to ask you which one is the solution to this differential equation. What would you do? How would you go about solving this?
I'll try to find where is the y equals 0.
That's a good thought.
I was gonna say take the y, the 9 sine x, and then try to get the double derivative for
Sure.
y prime, and then plug it in.
Perfect. Basically, let's check the solutions, right? So let's calculate y prime for each of these is going to be 9 sine of x, and then y double prime is going to be negative 9 cosine of x. And let's go through it.
Equations come from on the left?
These? Oh, that's going to be your choices.
Oh, okay, the choices.
Yeah. Now there's a couple more that I'm not giving because I want to get through this example in a finite amount of time, but on WebAssign, you can have 5 of them. All right. Just a little heads up there. I'm postponing the dreaded one in the middle. So y prime equals 9 cosine of x, y double prime equals negative 9 sine of x. There. What's dreaded about the one in the middle?
Multiplication.
Yeah, you got a multiplication, you got to use a product rule. Ugh. Gag. Whatever. Let's just suck it up and get it done. So, let's see. Y double prime, or y prime is going to be negative 9 halves. And I'm going to regard this part right here as being f, and then the second part is going to be g. So derivative of the first is just going to be negative 9 halves times the second, which is cosine of x, plus the derivative of the second, derivative of cosine of x is minus sine x, minus sine, or minus times this is going to be a plus 9 halves x sine of x. And this is the problem that just keeps on giving, doesn't it? Because now when we differentiate this, we get this one, but we got to use the product rule here too. So it becomes even more of a pain. I think I'm going to run out of space. Let me come down here. Y double prime is going to be negative coming from the derivative of cosine. Is going to give us a positive 9 halves sine of x plus 9 halves sine of x minus 9 halves x cosine of x. And at least these two combine, right? These two are like terms. So overall, I get that the second derivative here is going to be 9 sine of x minus 9 halves x cosine of x. Whew. That one's kind of a pain. More of a pain than I really wanted. So you can test each of these in here until you find the right one. That's kind of probably what you're going to have to do. So let me take a guess that it's this last one here, or the middle one here. It's actually going to work. So that means I'm going to have to plug this expression the y double prime into here and see if it works.
Professor,
Yes.
don't you have to do the product rule for 9.5x sine of x?
I thought I did. And that,
I don't think there's a minus.
Oh,
Is there?
that, this right there. So the derivative of this was this. Derivative of this, I used the product rule here.
oh, I see.
So the derivative of that would be 9/2 times the second, which is this. Derivative of the second is going to be a cosine. Did I screw up? Do I need a plus here? Your sine is cosine, so I think I might need a plus here. Yeah, I think you're right. Through the first, through the second is cosine, so yeah, that should be a plus. So there'll be a plus there. Thank you. Let's see if this works. Okay, so yeah, I think that's going to make a beautiful difference. So we'll plug it into y double prime plus y equals 9 sine of x. So plugging in y double prime is going to be 9 sine of x plus 9/2 x cosine of x plus y, which was what we started out with here, which was minus 9/2 x cosine of x. And that should equal 9 sine of x. And let's see if it does. Well, those cancel each other out. So yes, it does equal. Whew. I'm glad that worked because I didn't really look forward to trying a couple other ones. All right. At home, maybe a judicious guess there would help you out. Couple more problems to finish out this section and show you a little bit more variety here. Any comments on this one? Hoping that one's not too bad. It's just basically some work from Calc 1. Let's see, do I have this one up here? Okay, so what they want you to do and what will be helpful in some of these problems is show a family of solutions. So sample y equals 2 ln of x plus c over x is a solution to a differential equation. Now you're going to see a lot of constants used in upper level math, used and abused. And I don't know, I kind of delight in some of the sadistic ways we abuse these constants, but that's not reflective of my personality in general. Nonetheless, we need to understand what some of these graphs look like for different values of C. Now, you could program in this for C equals 1 into your calculator and C equals 2 and 3 and stuff like that. And you can do likewise on Desmos to see what a bunch of different values of that constant would look like. You get a family of solutions. Family of solutions. And they're all going to look pretty similar, just going to be different from each other by a constant. Now let's see what they look like. Now I've set that up for you, and did I send you the link to this page here? No? Yes? No? Give me some feedback here, please.
No, I don't think so.
Okay. All right. So let me put this in the chat here real quick. There we go. Okay. So I'll give you a second to open that up if you're so inclined. But I want to look at this for different values of C. And what I did in Desmos is I typed it in with just a C here. But I'm going to define C below. And here's the cool part that Desmos just rocks at, is being able to show you a whole family of solutions. Now, somebody give me a value of C that they want to type in here. I mean, nothing really off the charts, not like a zillion, but throw out a value.
7.
7. All right. So I'll put in a 7 there, and I see some solutions. How about another one? What else? 4. Or 5. And as many values as I want to put a comma in for, I can get solutions. 2, 1, 6. So there you go. I got a whole family of solutions. And if you zoom out a little bit, now I'm going to zoom out by putting my cursor near the y-axis and zoom out this way. And I can see more of what's going on with these solutions. So that's cool. Now if you put your cursor on the x-axis, hold the shift key, and then zoom in the other direction, that's kind of cool. That's what my family of solutions looks like. And you can just put in whatever values of C that you want. And one of the things that they're going to ask you is, well, what's the family of solutions look like? Now you've got two choices. You can either plug in a bunch of values for C and do it kind of on your graphing calculator, or you can do something like this. If you're not comfortable, if you don't feel cool doing this and using the little square brackets, you know what? You can do this. Let's just copy this, paste it, and I'll put an actual value like, I don't know, 8. And then I can repeat this and put in a value like 9, and so on. So you don't have to get super fancy with this, but I find it handy. I find it very convenient. More important for us in this section is that they're going to ask you to find the value of C for some initial condition. So let's check in on that. I've got to get back to the right page. So they're going to give you some information like this. They're going to tell you y of 3 equals 1. Then you're going to have to solve for C. Because what are they telling you? They're telling you when x equals 3, the y value equals 1. So let's put in everything and solve. So with that, I get 1 equals 2 times the natural log of 3 plus a constant divided by, well, x is 3. So I get that. Great. I want to solve for C. So the first thing I can do is multiply both sides by 3. You get 3 equals 2 ln of 3 plus a constant. If I want to solve for C, I can just move that to the other side. 3 minus 2 ln of 3 equals C. Now I can plug it in there and move from a general solution to a particular solution. the solution that's particular to this initial type value, or at least the function passing through that point. So it should look like this. Y equals 2 ln of x plus 3 minus 2 ln of 3 all over x. So all I did here was I replaced c by that right there. Nice.